So in this lecture, we're going to talk about caches. And caches are important because they give us more speed. Today we have DRAM, our main memory, which is very slow compared to the processor. And by using small, fast caches, we can make it look much faster. So we're going to start out talking about the memory hierarchy. That is, how are we going to provide a memory system that is both big and fast? And the way we're going to do this is combining small, fast SRAM memories with larger, slower DRAMs and disks. We're going to talk about how we do this by caching. The idea is in caching is we have small memories and we put the important data in the small memories, that is the data we're working on. Then we can access that data quickly and the processor runs faster. We're going to walk through an example of how we cache instructions for that. Then we're going to talk about some details of how a cache works. We're going to talk about tags, which are used to identify what is in the cache, and the cache blocks or lines, which is used to make the cache more efficient by storing more data in the cache. Then we're going to go over how you make caches practically. Talk about 3 different types of caches, from fully associative to set associative and direct map. Talk about replacement policies. That is, how do you choose which data to kick out of the cache when you need more space, and write policies. How do we write into the cache? And finally, we're going to discuss cache performance. So let's begin talking about the memory hierarchy. So what's the problem that we're going to solve with this memory hierarchy? Well, it's that we want our memory to be big and fast. And this isn't just nice to have a big and fast memory, but we need it. We need to have a big memory because the ISA has promised a large memory. We have a 32-bit address space, which means the ISA tells the programmer that they have 4 gigabytes of memory to work with. And even if we're running on a machine with less than 4 gigabytes, we still need to support that. We also want the memory to be fast. We want it to be fast not just so our programs run faster, but because we do lots of memory accesses. So 100% of instructions are going to load their instruction from memory, and 33% of the instructions are going to load data or store data. So that means we're doing lots of accesses to memory as we execute our program, and we need them to be fast. The problem is we don't really have the right stuff to work with. We don't have any technologies that are both big and fast that we can use to build our memory. So here's what we do have, and this is from the lecture on I/O. So we have disks, which are very large, but they're incredibly slow. So big, but not fast. And we have SRAM, and SRAM is very fast, but it's incredibly small. So here we have fast, but not big. So we don't have one technology that's both large and fast. So how can we put this together? We start out with, we have hard disks, which are very large and very slow, flash and DRAM, which are in the middle, and then SRAM, which is very small but very fast. And we need something that's both fast and big. So from this, it's clear we can't use just SRAM because it's too small. We can't use just DRAM because it's too small and too slow. And we can't use just flash or hard disk because it's way too slow. But what we can do is we can combine these together. So we can combine them to get the speed from small SRAMs and the size from large DRAM and hard disks. This combination is the memory hierarchy. So we're going to use these different technologies, put them together, use them in a clever way to get the best of all of them. So let's take a look at the memory hierarchy. You can see here we're going to start at our CPU, and we're going to use small amounts of fast SRAM. So we hook up this small amount of fast SRAM. Maybe this is 2 megabytes of SRAM. It's very fast and it's very small. We're going to use lots of slow DRAM. So we'll hook this up to a lot more DRAM, maybe 2 gigabytes of DRAM, which is much larger, but it's also much slower. Then from there, we're going to put in an even larger amount of very slow hard disk. So here we go up to 2 terabytes of hard disk. This is very large, but it's also incredibly slow. So what this does, this hierarchy creates the illusion of having a very large memory because we can fit as much as the largest part, the 2 terabyte hard disk, but it will also seem very fast on average. And it'll seem very fast if we're clever about how we use it. So to do this, we want to keep the important data in the fast memory. So the data that we're working on right now, we're going to move all the way up to the cache so the CPU can access it quickly. And the data that we're not using anymore, we want to move out to the slow memory to make space for the fast data in the fast memory. So let's take a look at an example, video editing. So here's our small cache. We've got a medium, large, but slow DRAM, and then we've got a very large, but very slow hard disk. So when we do video editing, we have lots of data. So this is too large to fit in the DRAM, so we're going to store it on the hard disk. So here's our movie. Now, when we're going to go start editing this, we're going to take the part that we're editing and move it into DRAM. So here's the part we're editing, and we're going to go ahead and move it into DRAM so we can work on it. Now the CPU is going to load just the part of that it's actually working on right now into the main memory. So if it's working on the top part of this video frame, it's going to move just that part into the cache to work on it. Then when it moves to work on another part, it's going to move just that part into the cache as it works on it. When we go to work on new data, we're going to move that new data into the DRAM as we process it. So when we go to look at the next frame, we're going to move that next frame into the DRAM and get rid of the frame we had before. So remember, the key to making this work is we need to keep the important data, that is the data we're working on right now, in the fast memory, so in the cache or the DRAM. And we need to move the unimportant data out to the slow memory to make space for the important data in the fast memories. So the key here is we have slow and fast memories, and we need to move the data around at the right time to the right place. So let's take a look at the memory hierarchy in processors today. Here's an Intel Nehalem processor. It has 4 cores. Here are the 4 cores. Each of those cores has a very small level 1 cache. So here's the very small level 1 cache. It's 32 kilobytes for data and 32 kilobytes for instruction. They have much larger level 2 caches. So a 256 kilobyte level 2 cache. And then the whole chip has a much larger level 3 cache that all of the cores share. So here's the 8 megabyte level 3 cache. And then finally, all of these are hooked up to an enormous DRAM off on the side. So if we look at how long it takes to access these memories, we see that the first cache takes 4 cycles to access. The second cache takes 10 cycles. The third cache takes 40 cycles. And we go all the way out to the DRAM, it takes 200 cycles to access the DRAM. So this is why it's so important to have this memory hierarchy. If we didn't have these caches, all memory accesses would take 200 cycles to access. But by trading off size and speed, we can provide a hierarchy where if we use it efficiently, we can make it look very fast and very large. So it's actually worse than what I showed you in the picture before. Let's take a look at the historical trends. So here's how fast processors are getting faster, enormously faster. And this is because we can just put more and more cores on them and they can process faster and faster. Here's how fast DRAM is getting faster. Not nearly as fast. So what we see from this is processors are getting faster, far faster than DRAM. And this is leading to a gap. So this gap here between processor speed and DRAM speed is making memory seem slower and slower. If we can run our processor faster but we can't run our memory faster, then the memory seems slower. So this makes the memory hierarchy more and more important. As memory seems slower and slower, it's more and more important that we do the right thing with caches. So let's review what the memory hierarchy provides. We have a CPU with a very small, very fast cache, larger but slower DRAM, and a huge but very slow hard disk. And this memory hierarchy provides very fast access to memory, but only if we have the right data in the right place. It provides very large memory, so we can fit as much as we have on the hard disk, but it's possibly very slow. And it's reasonably cheap. So we used lots of the cheap stuff in this hierarchy. When we built this computer, we put in a big hard disk, and that's a pretty cheap way of storing stuff, but only a little bit of the expensive stuff. The SRAM and the DRAM are far more expensive, and we use far less of them.